We're going to try this from my laptop today.
Sure. It's got to be better than the other camera.
Yeah, the field of view is already better. Hot dog. I'm tired of waiting around for this computer. I'm tired of logging into it. Just so. I'm going to derive all of relativistic MHD today.
Sounds like fun.
Hey, look. Does it work? Work? Oh, somebody just got a free black marker.
What the hell happened to the board before though?
Someone used a Sharpie.
Okay. Pink one, not bad.
Yeah, doesn't really go on very well.
There's like these alcohol type like things that work on me, so it's not work really well. But
Indeed. And
I don't feel like.
Okay, yeah, you're already now.
all right. I expect that I have more notes written up than we can hope to get through. So I think I'm going to reorder them a little bit.
That's been true on every time except
I get through almost all of them. Not egregious.
I think it was one of the times when I wasn't here.
Yeah, I think we'll reorder this a little bit. Then if there's time, we'll come back to that. Oh, how's it going? Let's get started on implementing this. After today, we'll have all the equations in hand. Today, I'm going to work out a Riemann solver as well, or at least write down how you actually, for one particular Riemann solver, compute the numerical flux. And I'm going to do MHD today, and it's going to be a little more nuts and bolts than what we've done before with the hydro stuff. I'm going beyond what the book has. You asked for MHD and transport.
I asked for transport.
They asked for both.
I wasn't here.
Kyle's like, I had no part. I had no part in that decision.
I mean, I'm fine with both. I did it.
Oh, see, I heard it the other way around. Oh, wanted to skip both. This might be the last lecture we do before we move on to some black holes and event horizons. But today will be very nuts and bolts of how you implement an MHD method. But it's completely applicable to a pure hydro method. You know, you just set B equals 0. Bob's your uncle.
Speaking of topics that we'll be moving on to, the schedule, since things are a little pushed back, you have many question marks next to binary neutron star initial data. Or possibly do that instead of like binary black hole initial data.
Well, you know, this is actually a good conversation to have. So, in point of fact, since we have spent so much time on MHD and matter source terms, we might actually be better disposed to talk about binary neutron star mergers instead of binary black holes. Binary black holes are simpler, but we've developed the MHD stuff, which it's like, okay, binary black holes are just evolving space-time. Once you put matter on there, then you've got to deal with the MHD aspects of it and talk about, you know, we can even do neutron star mergers with a polytropic equation of state, sort of. So instead of doing all the chapters and all the stuff on binary black holes, what I'm saying is that we could instead do it all on binary neutron stars.
I wouldn't be against that.
I think most people here care more about matter than vacuum spacetimes.
Also something
Kyle wants both. I can see it. He's like, let's do it all. Can we have extra lectures?
Yeah, it's also one of the things that we work on this, partly on this summer, doing initial data for the binary star mergers.
Okay.
It sounds useful. More useful than black holes.
It's really relevant to what I feel.
You're just not thinking creatively enough about your research.
I don't know, until we like start producing neutron stars and colliders.
But we do. We do. Collider here. Oh, hey, Howard. Yeah, shut that. Yeah.
I mean, slam enough mass together where it almost makes a microscopic black hole that's slightly too big. It's like a microscopic, right?
Yeah, but it'll dissipate quicker than.
We hope.
Just make it move faster.
We hope.
It'll stay around forever.
All right. Let's kick this pig. And if you're looking at the notes online, sorry, I uploaded the wrong file. I'll fix that. Okay, so we'd already kind of introduced the main players in this passion play with the Faraday tensor and the magnetic field in the co-moving frame. So let's go ahead and get to some evolution equations. We'll do that, and then I'll introduce what's called the Valencia formulation of relativistic MHD, and write out all the steps and equations necessary to actually stick this into a computer and get something like an answer. If we get through all of that, I'll even talk about a couple ways of maintaining div B twiddle 0. If we get through all that, which is a big if, I'll come back and talk about what about in the non-MHD limit. So who wants to give me, what do I mean by the MHD approximation? What's approximate about MHD? Infinite conductivity. What physical implication does infinite conductivity have? I may or may not have said it directly last time. That's right. Yeah, anybody can answer. No electric field in the rest frame of the fluid. Another way of saying that is that field lines are frozen in. Magnetic field lines are frozen into the fluid and they move with the fluid. They are advected with the fluid. There is no diffusion of the magnetic field with respect to the motion of the fluid. Okay? So that's the MHD approximation. So that can break down in certain interesting regimes. For instance, what if you get to the edge of the neutron star and you pretend that it's vacuum outside the neutron star? Well, in the MHD limit, if there's vacuum, there's no matter. You can't have MHD there. You're missing the H part. And so you have to do something else. We might come back to the full equations. It's just Maxwell's equations, right? We might come back to that. So let's stick with the MHD, and in particular, ideal MHD, this limit of infinite conductivity. You can actually add things to MHD, still making the MHD approximation that relax the ideal aspect of it, and then actually allow magnetic fields to diffuse with respect to the fluid. That's things like resistive MHD, where you add resistance. That's just diffusion, really, of the field, and Hall MHD, but we won't talk about that. So let's start by defining the dual to the Faraday tensor. We're going to denote that by F star AB. So I'm going to put a little star up there representing the dual to my Faraday tensor. 1/2 the Levi-Civita ABCD times our regular Faraday tensor. And then we can use the definition of the magnetic field in the co-moving frame based on the Faraday tensor, which I guess I'll just write it up because we've got it. So B in the co-moving frame, which I'll denote with that little u, meaning it's moving with the forward velocity of the fluid, right, is 1/2 the Levi-Civita ABCD of U, B, F, D, C, okay? So that's the definition of our co-moving frame magnetic field. With that definition, we can turn this dual, F star AB, into the following. That's going to be equal to UB, BA in the co-moving, minus UA, BB in the co-moving. Like that. Right? Easy peasy. And then from this, we can get the magnet, Maxwell's equations. Now I'm calling these the magnetic Maxwell's equations because the electric field doesn't appear, because in the co-moving frame it's 0. And those arise from taking the divergence of the dual to the Faraday tensor, and it must be 0. It's a conservation law, right there. That leads to an expression of partial with respect to A of square root of minus G, the determinant of the 4 metric, times UC BA in the co-moving, minus UA BC in the co-moving, equal to 0. Now, we're going to define the following. A new magnetic field variable, little b a, and that's going to be equal to this co-moving frame magnetic field over the square root of 4 pi. It is just a rescaled, conveniently rescaled. It's a units thing, right? We want to get rid of the 4 pi's and ignore permittivity of free space, et cetera, et cetera. And we can also define our spatial velocity, just reminding you, in the usual way, where we take the 4 velocity and divide by the time component. This gives me partial with respect to A, gamma to the 1/2. Yeah, this is where my notes cut off, so watch me and make sure I don't make a mistake. VC BA minus VA BC close equals 0. Somewhat simpler expression where we've got our Lorentz factor W and the determinant of the spatial metric, square root. Okay, so now we're going to introduce a new magnetic field component. Which one am I going to call this? Right, it's the Eulerian frame magnetic field. I'm going to call it a curly B. Apologies for all the different B's, but this is the nomenclature that is used. And this is going to be equal to the square root of 4 pi, gamma to the 1/2, Lorentz factor W, BI minus VI BT. Okay. This is essentially the spatial component of the full magnetic field as observed by a normal observer. So basically, it's like an Eulerian frame, right? And in terms of what that means then, is that this is related to our full magnetic field simply by square root of the determinant of the spatial metric. Okay. Now, we can split this equation into 2, right? So this includes a time derivative as well as spatial derivatives. So in our usual 3 + 1 trick, we're going to split this into time and spatial components. So setting the index here equal to the time component, what we will get, so if you look at this, set that equal to the time component, that goes to 1, right? If we set C, let's just set C, let me spell this out explicitly. Set index C equal to time. So that goes to 1 because V0 is 1 in this case, right? That's just 1, no problem. And so all we end up with is this component over here. And what that then is, it leads to the solenoidal constraint. It basically just says this. After a little bit of algebra, you get rid of that, and then what you recognize is that that is exactly this, right? This goes to 1, that's this. I substitute this in exactly for there, right? And then all I have is the divergence of this thing, which I defined, right? Because that goes to 1, and then all of a sudden it's exactly this, right? And that goes to time, it's exactly this. And so this is just why it's why I defined this quantity, so that I can make this, okay? Divergence is 0. That we're going to call, of course, the solenoidal constraint, or the div b equals 0 constraint. But this is a constraint equation for MHD. Now, if you set C equals to I, we'll get our spatial part. Set C equals I, and you get the spatial part of that equation, which is nothing but the induction equation. So partial with respect to time of BI, and then now I'm splitting it up into the time and space components, right? Partial with respect to J, the spatial part, VI, these are curly B's. I can make my substitution, right? After I set this equal to C, I can substitute that in and use my curly B's in here. Bj minus Vj Vi, all equal to 0. This is the induction equation. Tells me how the magnetic field evolves in time, like that. Okay. Now that we have those definitions in hand,
Yeah. Those the beta,
the curly
B.
cursive B's. So this one.
Alright.
This one. I will try, if that gets confusing, most of what follows will be curly B's, but in some places it will not be. And so if it gets confusing between my print B and my cursive B, let me know. Maybe I'll make the cursive B a little more flourished. Huh? An extra letter for B, yeah. Okay. So, all right, let's dive in here. Remember all of these. Let's go here. Remember these equations. Remember these definitions. I'm about to use them. Okay. So this is going to be now the Valencia formulation. I'm not doing my Castellano correctly. What you're going to see here is based mainly on my friend Phillips' paper, 2014, and the references therein. Of course, this is not the original reference for the Valencia formulation, but this is the one that I'm following for today. So go see Phillips' paper for some details. And I will leave out details that are actually in the notes. The notes are a little more self-contained, but we've already talked about some of the definitions that I rehash in the notes. Okay, so let's start with the hydrodynamic contribution to the stress energy tensor. In general, we've had this before, but I'll just write it down. So TAB hydro with a capital H, we've had this before. It's rho times the enthalpy UA UB plus P times the 4 metric, like that. Where sticking in my definition for enthalpy, I have rho plus rho E, which is the specific internal energy density, plus P. There's my enthalpy. UA, UB plus P 4 metric, GAD. Had that before. The EM part of the stress energy tensor, we've had this as well. I'll just write it up here. TAB EM is equal to Faraday tensor FAC, Faraday tensor upstairs B, downstairs C. Minus 1/4 4 metric GAD times FCD FCD, the inner product of the Faraday tensor, like that. Okay? Now, using the MHD approximation and substituting in my definitions that I had before for the magnetic field, dropping in the electromagnetic field part, I can write this as, that was an e-common, B squared UA UB, like that, minus BA BB plus B squared over 2 times GAB. So again, in MHD, electric field drops out, everything depends on the magnetic field. Here I've written my rescaled magnetic field. And of course, B squared is just BA, inner product with itself, which we're going to define to be 2 times M, PM, the magnetic pressure. Like that. So that B squared is 2 times the magnetic pressure. Don't forget that factor of 2. Can really screw you up. Okay, so the total stress energy tensor then is, in this case, TAB is equal to the sum of those two things, right? So you can just add those together, and we're going to, I don't need to add them together for you, you see what they are. I'm going to use my definition of the pressure there, and I'm going to rewrite this then as the following: rho times H star UA UB plus P star GAB minus BA BB, where H star is defined as 1 plus epsilon plus P plus B squared over rho. So that's a generalized enthalpy, which includes the magnetic contribution. And then where P star, you can guess where this is going, is just equal to P plus PM, which is simply equal to P plus B squared over 2. Where P is the gas pressure, hydrodynamic gas pressure, okay? So then we will say that the spatial magnetic field, which is what we had before, I'm just redefining it. It's the same definition, which is another way of saying it is the Eulerian component of the Maxwell tensor. That Maxwell tensor is the dual to the Faraday tensor. That's what that's called. So this looks like this. So B non-script B is in A, our normal vector, FIB, like that. That can't be right. This has got to be an A up here. Okay. And in the end, this has got to be equal to minus the lapse F star I 0. So it's the Eulerian component of that Maxwell tensor, which is the dual to the Faraday tensor. And recall, just for completeness sake, that the components of the normal vector in 3 plus 1, just the lapse, minus the lapse, and then zeros in this case. Okay. So now let's get down to the evolution equations for my complete system. So these are going to be derived from our conservation laws. In particular, I'm going to call this mass conservation. You could conserve instead baryon number, for instance, right? We've talked about that in a lot of cases. Now let me define J for you. But here we're taking it from mass conservation, which, right? So JA is equal to rho, the mass density, mass energy density, times the forward velocity. And this is the mass current, or flux, if you will. Okay? And then it's also derived from our old friend, mass energy momentum conservation. Grad of TAB is equal to 0. Just like all the equations of hydrodynamics and MHD we've derived so far, they've come from these general conservation laws, like this. And then finally, in our case, we also have to include Maxwell's equations, which come from the Maxwell tensor, specifically its divergence being 0. And these are the way to express Maxwell's equations in a geometric relativistic form in general, like that. So from those, hey, like what? Come on. That wasn't an equation. It wasn't an equation. Okay. Like that. Okay. So using these, we can write down in 3 + 1 our evolution equations. All right, so let's set up a set of conserved variables. Remember, we have some choice in our conserved variables. What we're going to follow here is pretty close to the Wilson formulation, actually, which the book more or less uses as well for their MHD derivation. And this is pretty closely related to this. I've just written it in a slightly different way. So this is our vector of conserved variables. And like the Wilson formulation, this is chosen so that the final form of the evolution equation takes a nice flux divergence, flux conservative form. So we're going to have D, which is square root gamma rho times the Lorentz factor. We're going to have the momentum vector, which is square root gamma rho times now our generalized enthalpy, W squared, the spatial 3 velocity, Vj, minus alpha Bt, the time component of our magnetic field, Bj. An energy variable, tau, square root gamma, all times rho times the generalized enthalpy, W squared, no velocity, minus P star, our generalized pressure, minus alpha times the, time component of the magnetic field, Bt, all that squared minus D, because we want to subtract off that mass part so that we just have energy there, right? And I should say that this is, this is slightly different notation than we've used before. This really is the mass density, not the mass energy density. Right? Which is why we're subtracting it off here, because I want tau to be just my energy variable. Wilson did this as well, right? Okay, and then our usual, there's my script B, which is just square root gamma times that Eulerian component of the spatial magnetic field. Or, well, the spatial magnetic field, which is the Eulerian component of the Maxwell tensor. Okay. And then in these, just for the definition's sake, are 3 velocity, which this is a slightly different definition for 3 velocity, ui over w plus beta I, the shift, overlaps. And w is 1 minus vi minus 1/2. 1 over the square root, right? That's our usual Lorentz factor, just like that, okay? This is more or less equivalent to what we've been working with before, but numerically in the code, this is what gets used to compute the spatial velocity. Okay, so now, starting from these equations, we can write down the conservation laws. I won't do the full derivation. Okay. So evolution in what's often referred to as flux conservative form, where we try to write this down in the form of a conservation law. And so that looks something like this, where we've got partial of some solution vector with respect to time plus partial of some flux vector with respect to space, xi, is equal to some source term vector. And the nice thing about that form is that it's a first order PDE. We know how to solve those. We can do that. So taking this form for our evolution equations, what we find from the conservation of mass and the conservation of energy momentum and from Maxwell's equations is the following. Our solution vector takes the form d sj tau and script b k, obviously transpose for the vector. Question is, will I be able to keep this up on the board? I'm going to try. I'm going to try. I will fail probably, but I'm going to try. Okay, let's write it here. Got lots of room. Okay. So now our flux vector then is going to be equal to the following. Alpha times a bunch of stuff. The very top, d times v I. Right? Sure, I should have an I there. I don't in my notes, but I'm sure I should. Sj v tilde I, which I'll define in just a second, plus the square root gamma p star delta function ij minus bj, little b, script bi over w, and then tau v tilde I plus the square root of gamma times p star vi. Yeah, I agree. Minus alpha bt bi script b over w. Sorry for the delay. This is where my notes got cut. So I have to think very carefully. Don't like having to think. Hurts. Vi tilde minus bi vk. Close bracket. Close bracket. Now, obviously, you recognize this directly from the induction equation, right? This is our energy conservation. And so these are fluxes of my conserved variables. If you plug this into, the conservation laws, this is what you get out. Okay.
It'll be tilde on the last term too, or no?
Of course it is. Of course it is.
And also same question on the one right above it, the whole term. Or is that one just a v?
Let's go with sure. I need to double check that because
also the one on top for that matter.
I need to check that. I might have got lazy in my notes, or they are actually different. I need to verify. Okay, hold on. I'll double check. Oh my goodness. We're going to get through a lot today. They are. Oh, look at that. Okay, so either that is a tilde, but this one is not. So either Philip might have had a mistake in here. That is weird that they're all tildes except for that one.
Well, I guess we should probably see what the definition of that is first. But
yes, of course.
It's just weird that, at least in the last one.
It is. It is. So in Philip's paper, this one is not tilde. The rest of them are. Obviously, for symmetry purposes, this had to be.
Yeah.
This had to be. Okay. And now the source term. I'm off the edge of the board. So the source vector is equal to alpha times the square root of gamma, all times. Source term for mass conservation, big fat goose egg. Source term here, TAB for the momentum equation. The divergence of the 4 metric minus the connection coefficient, CAB, times the 4 metric CJ. Like that. Alpha times TA0, the spatial gradient of the natural log of the lapse, minus TAB, connection coefficient 0AB, and then for the magnetic field, 0 vector. Like that. So those are the source terms, right? And so here's gravity acting on the momentum and energy, right? Okay, and then
Just to clarify, these connection coefficients, these are for 4-dimensional, not 3.
that's correct.
Okay.
That's correct.
We had the other notation before, so.
Yep. This is the related to the 4 metric. These are the connection coefficients related to the 4 metric. Okay, and then V star or V tilde I is going to be defined as VI minus beta I over alpha. So the shift over the lapse. Just a rescaled velocity there. All of these then are supplemented by the solenoidal constraint, which we get from the divergence of Maxwell tensor 0B must be equal to 0, which leads us to 1 over the radical of gamma, the divergence of gamma BI, that's now just the spatial part of the magnetic field, is equal to 0. Given my definition for script B, this is synonymous with the divergence of script BI equals 0, which is just div B equals 0. That's all that is. Yeah, that is probably not necessary. So I wonder about this. We'll have to double check that. That bothers me. I'm looking at the archive version of this paper. It's probably been fixed in the print version. Okay.
It seems unnecessary to have to carry both those around.
Yeah.
Or have to convert.
Yeah. You wouldn't want to do that. I think it must be. I'll have to take a look. Okay. So satisfying this constraint, we're going to talk about 2 approaches later. One is something called divergence cleaning. And that's the first one I'll talk about, not immediately. Where the idea is, you'll see this, we add a scalar field, a fictitious scalar field, which advects away the errors in the divergence, and then it has a parabolic term that damps them in time. And so you move the error away. You generate divergence in magnetic field, but then you take it away from the problem at the fastest speed, which is usually the speed of light in these cases. The other way is something called constrained transport. There's a whole class, a whole family of methods under constrained transport, where you construct numerical solutions to the MHD equations that preserve div B equals 0. They don't make it 0. They just keep it, they don't let it change. And that's actually an important distinction. So that means even with constrained transport, if your initial conditions don't satisfy this, your evolution will not satisfy this. because what constrained transport does is they keep this from changing, whatever this is. If this starts out as 0, then to machine precision, usually it's 0, but it actually depends on the constrained transport method. So the one that I will talk about today, which is implemented in Phillips code, it's called flux CT, or flux interpolated CT. And that actually maintains it to truncation error of the scheme, which is not machine precision. But hey, it's good enough. Everything else in the problem is to truncation error as well, so whatever. Okay. I think that's unnecessary, is what I think. Okay. So let's move on to solving the Riemann problem. So we've talked about this before in the context of hydrodynamics. Last time, I think, or the time before, whenever we were talking about hydro. The general approach here is I've got this set of conservative variables. They obey this PDE. I need to solve, for the time evolution, I'm going to bring this term over here. I need to compute the source terms, and I need to compute the divergence of the flux to do my time evolution. Now, in finite difference, I could do that just directly working on the pointwise values. What we're going to do in flux conservative, it's finite volume method, so we have to compute the evolution of these averages based on divergence of fluxes at faces of the cell. So let's draw a picture. Show you what I mean, right? Very simple picture. I'm going to draw a grid on the board. Anybody? All right. So let's say these are two neighboring cells in a two-dimensional finite volume approach. I've drawn X's at the cell centers, but keep in mind that in a finite volume approach, you're actually evolving the cell average, which to second order is the cell-centered value. But beyond second order, it's not necessarily the cell-centered value. But what we do first is we reconstruct to the interface. We take the average values and we construct pointwise values at the interface between cells. And we're going to do this from two different directions, right? And because I'm using two different interpolation stencils to do those operations, I end up with two different states which are nominally at exactly the same spatial coordinate by doing this. And they are at exactly the same coordinate, two different states. There's an infinite discontinuity between them, like a shot. We're going to call those the left and right states. Left on this side, right on this side. And using those input states, we need to solve the Riemann problem, which is a shock tube problem, to get the flux that's actually occurring across this interface. There's lots of approximate ways to do that. Probably the simplest way is just something called upwinding. I didn't actually write this down in the notes. But what you could do is you can interpolate your, okay. So this step is called reconstruction, right? We've talked about this before. And that specifically means taking cell averages and making pointwise values. That is distinct from interpolation, which is why we use a different word, because the math looks almost identical, different coefficients. But interpolation would be taking pointwise values to produce pointwise values. Here we're taking cell averages to make pointwise values. We're going to call that reconstruction. To distinguish it from simple interpolation like you might do in a finite difference scheme. The simplest approach is that you reconstruct these two states from your primitive variables now, right? These are my conserved variables, but my primitive variables are the things that appear in here. D and V and P and B. Those are my primitive variables. And then compute what these fluxes are on either side of the face. And then upwinding, you just look at the direction of the velocity, right? And you say, okay, whatever direction the velocity is going, that's the flux I'm going to pick and assign to the interface state, right? Based on the direction of the velocity. That's how you would choose. That's called upwinding. That's like the simplest thing you could do. Super duper diffusive. I mean, you want to see features spread out in your simulation. Do that. Super duper diffusive. So a much better approach is to actually come up with some approximate, even approximate solution to the shock tube problem, where you compute the characteristics and you look at the Riemann fan and you get some solution from that. For this, the one and only reference, Toro. I don't even know the year. It's a textbook. It's big, red, and expensive.
You can get for $25 if you log into the Springer web ebook thing through the MSU library.
There you go.
Also,
It's the same one we had last time.
yeah. I still have it.
It's the one and only.
Yeah.
It's the one and only. It has like all the Riemann solvers. And the Riemann solvers are general. You can usually write down, it's not always easy, relativistic variants of them. And one of the hard parts about generalizing a non-relativistic Riemann solver to the relativistic case is the calculation of the characteristic speeds, which we'll see here in just a minute. So the one that we're going to talk most about today, and it's probably the most simple, accurate, approximate Riemann solver, is the Harten, Lax, Van Leer, Einfeld version. This is universally simply referred to as HLLP. And it is a two-wave approximation. So in the Riemann fan, it pretends that there's only two characteristic waves, the fastest and the slowest, or the most negative and the most positive in that characteristic wave family, okay? So this is a, what we'll call two-wave approximation. I just don't see any way that I'm going to be able to keep those up on the board. Not in this classroom. Okay, and they're characterized by two wave speeds. So we only need two wave speeds for this. One, I'm going to call them xc. It's going to be xc minus, which is the most negative. So the one moving fastest in one direction. Pick a direction, whatever direction you want to be negative. And then the other one, xc plus, is the most positive. So the wave characteristic speed moving in the other direction at the greatest rate. Away from that interface. Okay. Commit these to memory. So I don't have to write them again. All right. Now, HLLE is actually very simple from here. Won't go through all the math of the derivation. You can go and look at Toro if you're very interested. But we'll assume this about the solution vector. Make some definitions based on our left and right states. So U, our solution vector, is going to be equal to the following. U, L, for the left state, if 0 less than xc minus, U star if xc minus is less than 0 is less than xc plus. And then finally, U right if, xc plus is less than 0. Like that. So you're basically just, this is why I didn't say left or right. You're picking which direction things are moving based on the characteristic waves, right? And that's how you build your solution vector. And then this intermediate state, the star state, usually referred to as the intermediate state. I should draw a Riemann fan. I didn't do this, but let me do it. I'll do it live, okay? It's a space-time diagram. This is time. This is space. And 0 represents our interface. And this event here is the initial event of the interface, right? And so time moves forward here. And so in this fan, I'm just going to pick some things. There is a characteristic that moves out this way, exceed plus, with that speed, right? So the slope of this thing is exceed plus. That's that characteristic. Other direction, exceed minus. Slope of that thing is exceed minus. Now, here on this side, you right. This side, you left. In between, you start. Did I get that right? That's what I mean by intermediate state. So as you go back at the initial point at this event, there's you left and you right simultaneously. But then as you propagate forward in time, because that's a shock, the shock propagates. We're assuming here that it is that the reworking of what's going on at this interface state is defined by just two characteristic waves, the fastest and the slowest, moving away from that interface. Here I've drawn them to be roughly equal. They don't have to be equal, right? They can, they don't have to be equal. But in between these two waves, there is an intermediate state, right? Almost like an averaging. It's not. Almost. But it's not. Okay, so U star is equal to C plus U right minus XC minus U left minus the flux operated on the right state plus the flux of the left state all over the difference of the wave speeds, XC plus minus XC minus. Yeah. So that's how I would compute these the intermediate state and the HLLE approximation. And then the numerical flux, which is the thing we really want, and this is at the interface, is going to be the following. That's, yeah, that's fine. F of U, which is what we really want to use for our solution then, is going to be equal to XC plus hat, and I'll tell you what that is in a second. It's just a limited speed, times the flux of the left state minus XC minus hat, times the flux of the right state plus XC plus hat, XC minus hat times each other, times U, the right state, minus the left state, so just the difference in those states, all divided by the difference in the hats. XC plus hat minus XC minus hat. And these hats are just limited characteristic speeds, by which I mean XC minus hat is equal to the min of 0 and XC minus. And likewise for XC plus hat is the max of 0 and XC plus. Sorry about that. But you get the point. So now that's HLLE. That's it. That's how you get the flux. Now the hard part is getting XC, right? In plain vanilla hydro, non-relativistic Newtonian hydro, this is actually pretty simple. Anyone know it off the top of their head?
Values over here. What if you said other matrix forms? It'd be like sound speed plus velocity.
Sound speed plus velocity, right? Take the greatest and the smallest of those two things, right? Any combination of the sound speed and the velocity, right? So greatest one, smallest one. There's my two waves. Easy peasy. It's harder in relativistic. So let's talk about how you get that. So getting them exactly is hard. Getting them approximately is easier and often good enough for numerical calculation. This is also only one of many possible Riemann solver solutions. And this is practically an analytic calculation here. This is easy. There are other Riemann solvers. This is not an exact solution. Exact solutions are iterative. They involve calculations with the equation of state and also multiple Conde prims, which are conservative to primitive conversions, which are hard in relativity. So this is a nice option. And the benefits of those other Riemann solvers is debatable. It's debatable. So this is often good enough for government work. Okay, which isn't that what we're doing? In the quick analysis of these wave speeds, we'll approximate these wave speeds, and they will be overestimates. And so this approximation will overestimate these speeds. And that's actually the safe bet. That's tantamount to adding diffusivity to the system, saying that things spread out quicker than they really should, right? So that's like adding a little bit of extra diffusivity. Now, diffusivity can hurt the accuracy of your solution, right? Especially if you're trying to maintain sharp discontinuities or sharp features, but it tends to make the solutions more stable. And so it's sort of a numerical or a numericist, dirty little trick, right? Well, this is not behaving. Diffusivity. Oh, now it behaves. Smoother. So it's a double-edged sword. Okay, so first we're going to start with an approximate MHD dispersion relationship, which describes how the waves behave in MHD. And that's going to be omega squared d is equal to kd, the wave number squared, times the alphane speed squared, plus the sound speed squared, 1 minus the alphane speed squared over the sound speed squared. Speed of light squared. I changed my mind. Get a little note there. Okay, moving on. Okay, and then this wave vector, Ka, we're going to define as minus omega, and then just the spatial part. And this is the wave vector and the dispersion relationship. Okay. So this all boils down to analyzing the eigenvalues. And CS is the fluid sound speed. C is the speed of light. And the alphane velocity is the square root of b squared all over rho h plus b squared, which is equal to the square root of b squared over rho h star. And that's the alphane, just to be alphane speed. Okay. So now we're going to construct a projected wave vector. Which is going to look like this. Big K, little a, is equal to delta function BA, UA, UB, all times the wave vector little k b. Okay. Almost there. This makes my the dispersion relation, this frequency, omega d, is equal to Ka, the wave vector, UA, which is equal to minus omega UT plus Ki UI. Like that. And so the wave number squared is the inner product of the projected wave vector, which is WD squared, the wave number, the wave speed frequency, for metric GBC, wave vector K, wave vector C.
Projected wave vector, one of those indices is not right. Because you're contracting on A,
Mm-hmm.
and contracting on B, unless it's capital KB equals.
You know, it's almost certainly this one. Yeah, and then that ends with an A.
Yeah.
It would probably be better to do. Well, B's fine there, to use a C here. That'd probably be better. That's just an inner product. Sorry. Does that make sense?
Yeah.
Okay. All right. Plugging this all in gives you a quadratic equation. Results in a quadratic equation to solve for Xc. In the end, this is what we actually care about. And this is a bit of a beast. Hold on. I'm missing something in this equation. And I almost know for sure what it is. Just 1 second. Yeah, right. Right. Got it. Okay. In the final quadratic equation we have to solve to get Xc is the following. Xc squared, where I haven't selected plus minus because there will be 2 roots to this quadratic equation. One of the roots being plus, one of the roots being minus. Lorentz factor squared, big V squared minus 1, which I'll define in just a second, minus big V squared, minus 2 times Xc squared, all times the lapse, Lorentz factor, V tilde I, all times big V squared minus 1, plus big V squared, the shift vector beta I, close, plus, open bracket, open parentheses, the lapse times the Lorentz factor, V tilde I, all squared, big V squared minus 1, plus V squared, alpha, all times the lapse, times the spatial metric gamma ij, minus beta I, beta I. Got confused there and I remember why. That's actually, and so this is my confusion. That's intentional. These are double upstairs indices. And that does not imply summation. Remember in covariant and contravariant, they have to be, one has to be upstairs, one has to be downstairs for summation. So this does not imply summation, and I'll explain that in just a second. Well, I'll explain it right now. This whole thing is equal to 0. And so the reason that this is not summation is that we get wave speeds in each direction. So there are different wave speeds in each direction, in the X, Y, and Z directions, which is why that's not summing. And so there's essentially 2 of them in each direction because there's 2 roots to this equation.
So same for the term before too, that alpha W V tilde squared, or V I tilde squared.
Right.
The first part of the last term, sorry.
Here. Wait. Here.
Yes.
Yeah.
Okay.
Yeah. Same there. Okay. Big V squared is defined as the outvein velocity squared plus the sound speed squared all times 1 minus the outvein speed squared. And xc is the resulting wave speed then from solving that equation. Yeah. And so that's the final step of the HLL Riemann solver. That gets you your characteristic speeds, most negative and the most positive, xc plus and xc minus, and then you just follow the formulae. Yeah.
So since there's no linear curve,
Yeah.
so they're same with flip sign.
Oh yeah, they're the same with the flip sign. That's right. That's right. One of them's got to be negative though.
We'd have z squared equals some constant at that point. So
Oh, that's right. To take this, you can have either the plus or minus, and so you can just choose which one, right? You have both. Yeah, that's right. That's right. You square minus 1. It's positive.
The magnitude is
The magnitude, yeah. Yeah, that's right. Thank you. Okay. All right, so now we've got our fluxes. Another step in the solution for the MHD equations is this conservative to primitive. I'm not going to put anything up on the board about that. Suffice to say, it's complicated. If you actually want to go and implement this, and we will hopefully get to a point where we're doing con-prim, but not for MHD. Unless you guys really want to dig into MHD, I'd love that. That's fun. We will have to do that, but there are, you just take an off-the-shelf thing these days. It's in Philip's paper. You can see it there. I think the book has some stuff on the prim as well. No, they don't really do it, do they? They
this
talk
one
about it.
does that relativistic hydrodynamics one does a little bit.
Yeah.
The result.
So suffice to say, it's hard, but there are some solutions that we can use. Stuff's in Philip's paper, and then also a more recent paper by Daniel Siegel, which also includes Philip Nosta on it, are good approaches to converting between conservative and primitive. It's tricky because it doesn't always result in a physical solution. And so you have to, that's one point where the solution can fail, is actually trying to convert from the new conserved variables to primitives. All right, so let's talk now about satisfying div b equals 0, which is the bugaboo in many a MHD approach. So first off, let's go with this one that is actually a little more complex to derive, but simpler to implement numerically, I think. Constrained transport looks a lot simpler on the page, but then when you go to actually put it in, it requires this bulwark of machinery in the numerical code to actually satisfy it. So divergence cleaning. Here we're going to advect div b out of the domain as fast as we can, and we're going to damp it in time according to something, some parameter. So we're going to introduce a new scalar field. It's going to look something like this. So I'm going to take my original Maxwell's equations, and I'm going to modify them. So I've got FAB plus the metric GAB times psi is equal to kappa, normal vector NB psi, like that. So in the limit of psi equals 0, which is my new scalar field, this is just Maxwell's equations. That's what it was before, no problem. So psi is going to give me my new scalar field that's going to take away div b, and this kappa is the parabolic damping rate. So you can actually take two limits here. Psi goes to 0, we're back to Maxwell's equations. Kappa equals 0, and this actually would just be pure hyperbolic cleaning. The kappa characterizes then the rate at which this error is damped in time, which we'll see here in just a second. Okay, So now, using F star AB is equal to 1 over W, the Lorentz factor, times UA BB minus UB BA. Those are the spatial magnetic fields, non-curly print. And B, non-curly, 0 is equal to minus the lapse times the 0, 0 component of the Faraday tensor now. And this is equal to 0 because this is the purely spatial magnetic field. So I can use that to simplify this equation. And then finally, what this will do for me, substituting these in to that equation, I'm going to get a new set of evolution equations, really, which we'll see here in just a second. Now, my induction equation that I had in the original set of equations I drew up here was from Maxwell's equations, right? From that. So now I'm toying with Maxwell's equations. So my induction equation is going to be different. And in addition to that, I'm going to get another evolution equation for psi by doing this. And so the first term on the left-hand side here with these definitions becomes grad A of F star A0 is equal to 1 over minus alpha square root gamma di square root gamma bi non-script. And then the second term becomes grad A GA0 is psi, of course, is equal to GA0 gradient of psi is equal to 1 over alpha squared all times minus the time derivative of psi plus the shift vector theta I times the gradient of psi. Like that. So putting these two together, we get a new evolution equation. dt of psi plus the divergence of alpha bi minus psi beta I. That should be an I, sorry. Partial I, because that's a divergence, is equal to psi minus kappa alpha minus di beta I, divergence of the shift, plus square root gamma bi di times, this is the gradient then of the lapse over square root gamma. So now this is my evolution for that psi. So I've got, and it's in the flux conservative form, right? I've got a flux here. I've got a source term here. Right? And so I can stick that in my evolution equations like before. And then, so this was the time component, right? I selected the time component here in both of these cases. So if I take the spatial component, I get a reworked Maxwell's equation and a reworked induction equation, right? So spatial part gives new induction. That looks like this. Time derivative of curly b, j, plus partial derivative with respect to I of open bracket, open parentheses, alpha v I minus the shift beta I, all times curly b j minus alpha v j curly b I plus alpha square root gamma, the spatial metric gamma ij, all times psi, is equal to minus curly b I gradient of beta j, yeah, plus psi times partial with respect to I of alpha square root gamma, gamma I j. Close. Okay. So if you look back in your notes, that looks a lot like what we had before. If you just set psi equals to 0, we're back to the same equation. Bob's your uncle. So we have a modified flux to the magnetic field. So when I go to compute my numerical fluxes for the induction equation, I have to include this modified part in the flux calculation. And then we have a modification to the source term in the induction equation, which I have to account for. But what this does is it takes the div B from B, takes it away. It says, you don't need that div B, you just give it to me, and I'll take care of it. That's what it's supposed to do. And the other thing that you should be talking about, or you should be screaming at me for, what did I forget to mention? The induction equation didn't have a source term, right? No, it did. Yeah, that's all right. But in the limit that psi goes to 0 and div B is 0, this is 0. Yeah. Yep. There it is. There it is.
The other term there cancels out the.
Yep.
Oh yeah, because the
Div B. Yep. Okay. Now this will perhaps modify your Riemann solver because you have to compute a new flux, and you might have to include a new wave speed, and you will. What is usually done is that a different set of wave speeds are used for this psi when computing the numerical flux in the Riemann solver. Usually you just take the speed of light. You just move that puppy out of there as quickly as possible. Okay, so that's divergence cleaning. Modifies your equations. Now, I am told that empirically, this method doesn't like to behave very well in full evolving metric space-time calculations. Likes to be very crashy. And so it's not as stable as constrained transport. It's simpler to implement, but it's not as stable. All right, so 5 minutes, we can do constrained transport in 5 minutes. Okay, so I think I will just talk through it with a picture. And then you can look at the notes if you actually care, or if you ever bother to implement such a thing, you can go and grab the notes and see it. So the usual way of doing this, so the idea of the constrained transport is to use Ampere's law, which relates the electric field and the magnetic field to each other, to create evolutions, time derivatives of the magnetic field that by construction obey div B equals 0. That is the idea. And so if I were to draw a picture of this, which let me just draw, I will attempt to do here. Come on, baby. Nope. No. Okay, I'm going to draw a cube like that. And in the middle of my cube, let's draw some back legs. So I got my cube. So this is my control volume, my three-dimensional cell in some MHD equation. In the center of this, I've got I, J, K, the cell center of this cube. in the very middle. At the face, I'm going to define at this face the x component of the magnetic field. All right, so let me draw my little triad. So my triad, oops, is x, y, z, like that. That's my triad. So that is only the x component of the magnetic field is defined at that face. And then at the edges, I'm going to define electric field components. Let me not use that. Let me use a script E for the electric field, Z. And then up here at the center of this edge, I'm going to define another component of the electric field, EY, and same down here. That's going to be EY, and then this is going to be EZ again. So now you compute circulation integrals, right? That's Ampere's law, is to compute the circulation integral and relate B to E. That's the idea. Now what you do in practice is you construct your numerical flux using what we had up on the board before. You get your Riemann solver, you get the solution for some numerical flux of B here, and you use those numerical fluxes to construct the electric fields on edges. And then you use those electric fields on edges to give you a new numerical flux for the B. But now, since you've used the electric fields in Ampere's law, that new flux of magnetic field must obey div B equals 0. So equation-wise, what does that look like? So what I do, once I've constructed this shenanigans, is the following. So we compute the time derivative of the face averaged magnetic field component, which I'll call B hat. That's just meaning it's face averaged. In the x direction at I plus 1/2 and j and k. That means this interface, right, half forward, with respect to time, is going to, delta y, delta z, is going to be equal to the following. So that's the change in the face area, basically. That's just the area of the face, right? Going to be equal to minus EY, I plus 1/2, J, K minus 1/2. So now that's the top one, right? Minus, I did minus, so that's the bottom one. That's this one, times delta Y, minus EZ, I plus 1/2, J plus 1/2, K, delta Z, plus EY, I plus 1/2, J, K. I got an index messed up here. Let's call that top one plus for the K. And then EZ, the electric field there, I plus 1/2, J minus 1/2, K, delta Y. So that's how I get that time derivative. These electric fields are on the face averages. And those electric field vectors are obtained from the numerical fluxes of the induction equation. That's what we get out of the Riemann solver.
You asked to delta y, delta z.
Of course I do. Thank you. Okay. And then all we do, so this thing gives me what I will actually use to update my magnetic field quantities for the cell center, wherever, right? There's two different ways of doing the constrained transport. There is one where you define the magnetic field as living at the space of the cell. That's how you define the magnetic field, in which case you directly use this equation to update it. Done.
The other way is to say, no, I don't want to deal with face-centered variables because it's a nightmare computationally. And that's true. And so you say that the magnetic field lives at the cell center and you average the fluxes in either direction. That's called flux CT or flux interpolated CT. That's actually what's done in Phillips code. All right, MHD. Yeah, Eric.
For this one, you may have said this, but the Riemann solver doesn't get changed for constrained.
That's right. That's right. So unlike the case of divergence cleaning, you don't have to worry about any changes to the Riemann solver, and there's no additional equation to solve. You know, we have that additional scalar field. There's also no extra terms in the induction equation. It is precisely as I had written it up on the board originally. I just modify what I actually use to update the magnetic field in the end.
So that right-hand side is a path integral on
Yep.
the Neptunian loop?
Yep.
Just a numerical.
Yep. Yep. It's a finite difference integral, path integral. Circulation. And it gets more complicated. So in Flash, my code, what I'm going to call the old solver for MHD, it's purely Newtonian, but it is a constrained transport and it's a staggered mesh constrained transport. And so it's the case where you define B as actually living at the faces. And then there's many different options for actually constructing the electric fields. So in one particular case, like I could directly use the flux from the Riemann solver to give me the electric fields. But what we actually do in many cases is we use the fluxes at several different neighboring zones around it to construct high order estimates of the electric fields on the edges. Now the solver that I wrote that you've used, everyone's used Sparky, that's actually divergence cleaning because I'm not smart and I like to keep it simple. And constrained transport is tricky, it's complicated. All right, overtime, thank you.